Thanks for coming along today to my session. I appreciate it's already been a lot of learning today, so thanks for spending the time to come to this one. My name is Grace Jansen. I'm a Java champion and developer advocate at IBM. And unfortunately, I speak no German. I'm based in the UK. My language skills are terrible, so please excuse me for that. So today, I'm going to be taking a look at addressing the transaction challenge in a cloud-native world. I will try and leave some time at the end for questions. If I don't get round to any, or you think of some later, for example, then please feel free to reach out to me on Twitter or on LinkedIn alternatively as well. My Twitter handle's here, and I have it at the end as well. So the first thing I want to consider is why we're even bothering to try and adapt our applications to be effective for the cloud. And that is because of this. Hopefully you're all Disney fans, just as much as I am. If you've not watched Toy Story, please go and watch Toy Story. It's an awesome movie. And it's because of this excitement that we get from this cloud, this excitement of, ooh, the cloud, the benefits that we get from it, like whether it be flexibility, whether it be cost optimizations, flexibility, dynamic scaling, all of these benefits that we can gain by utilizing cloud infrastructure. So we want to be designing our applications to be able to make best use of that underlying infrastructure. But when it comes to actually designing our applications to make best use of that, we often turn to methodologies, for example, like the 12-factor application methodology. And some of you might be familiar with that. Some of you might be familiar with the 15-factor app methodology, which is just an extension of that. And in this, when we start to look at methodologies like this, we start to see statements like, for example, the ones that I've highlighted, I've tried to make it easy, treat backing services as an attached resource, and execute the app as one or more stateless processes. And what this often leads to is this assumption that in order to be cloud native, we have to be stateless. We have to have stateless microservices. We can't have state stored. But what I want to know, is this really the case? Like, does this have to be a one-to-one relationship between the two? Can we enable ourselves to build effective microservice-based applications that are still able to have state? And for this, we need to have a definition of what I mean by stateless versus stateful, because it is not the same as serverless versus using a serverful. There are distinctions between these. And for this, I turn back to Disney, because what better explanation? Again, Finding Dory, please, or Finding Nemo, please go and see that movie. It is great. The animation is amazing. So in this movie, if you've not seen it, we have a little orange fish who goes missing in the ocean. His father, Marlin, on the left-hand side, is going to try and rescue him with the help of his very helpful friend, Dory. Now, these characters are actually great examples in terms of behavior of what it means to be stateful versus stateless. We have Marlin on the left, who has an excellent memory. So when it comes to responding to events that are occurring around him, Marlin stops, thinks about what's happened in the past. Perhaps when he's looking at jellyfish, he's been stung in the past, so he knows not to get too close to a jellyfish. He considers what's happened in the past and then reflects on that and acts. So he tends to be a bit slower when it comes to actually being responsive to events around him. Then we have Dory. Spoiler alert, Dory has no memory except the fact that she's a fish. So Dory is very responsive when it comes to events because she isn't considering anything else except what's in front of her. So Dory is a great example of that really fast ability to be responsive, just like stateless applications or microservices. Looking at a little bit of a more technical definition here. So when we're looking at stateless computing, really what I mean here is that the session information is not retained. So essentially, the state of the data isn't being recorded between transactions. What that means in terms of the architecture and the design is that when you're looking at things like recoverability and scalability, easier with stateless microservices, because you don't have to consider things like reinstantiating or reinitializing the state of that microservice if it's a replica, replicating that state from another microservice, or if it's recoverability, replicating it from before it went down. So this is a lot easier, and hence why a lot of people tend to go towards this direction for cloud native. Looking back at our friend Marlin here, so going back to stateful microservices, on the other hand, this is where we do retain all of the session information, so the state of the data is recorded between transactions. What this means when it comes to architecture again, is that it's essentially just a little bit trickier, there's a little bit more work to it, because we do have to think about the reinstantiating, that was a difficult one, the state of the data. And that's why it becomes a little bit more difficult. It can take a bit more time. And that's where that difference is between being able to respond very, very quickly. So you might be considering, okay, looking at these definitions, stateless seems to be much more in line with what we're trying to achieve in a cloud-native world. So why would we want to use stateful microservices in an application? Well, really, when we take a look at our applications, really what they are is just a reflection of what we want to do within society. So as a very clear example, booking a package holiday. If I was to walk into a travel vendor and physically want to book a package holiday versus doing it online, it is something that we want to do as a society, a behavior that we want to do that we would normally do. So realistically, it makes sense for our applications to mimic what we do within society, our behavior as humans. And our behavior as humans isn't stateless. Imagine a scenario where you forgot your partner, your child, your best friend's birthday. Like, that isn't going to go down so well. Definitely not for me. So it's important that we have things like important dates ready to hand without having to go and look at a diary to be able to respond to those particular bits of information. So realistically, it makes sense that sometimes, not always, but sometimes, we will need to still have stateful microservices or stateful applications, depending on what your application does. So when it comes to actually storing that state, traditionally what we might have used is transactions. What I mean by transactions is really just a group of read and write operations that either all succeed or all don't succeed. So they can either impact a single record or a multiple record, and a really clear, sort of very commonly used example is that package holiday that I was describing. So booking, for example, a hotel, some form of transport, whether that be car hire or if you're going fancy taxi, and some accommodation as well. And you can only have that package holiday if all of those resources are available. Now, traditionally, we might have used something like the ACID model for this. We work in tech. We love acronyms. I would know. I work at IBM. I like to try and describe acronyms because often it can be like speaking Latin. So if you're already familiar with ACID, just bear with me for 2 seconds. For those of you who aren't familiar, ACID stands for Atomic, Consistent, Isolated, and Durable. It is basically a guiding set of principles for how to build transactions that really focuses on that data integrity, making sure that that data is consistent. So that's why it has this really strong emphasis on this strong consistency and isolating those resources when they are involved in a transaction. So as I said, it's a guiding set of principles. It is intended to guarantee that data validity, that integrity and security. And when you're using something like ACID transactions, it will use something called a consensus protocol. So this is kind of like a voting system that occurs to essentially enable usually a central component to work out, okay, are all the resources available or are they not? Are we ready to go or are we not? And this consensus protocol essentially is what is the consensus among all of the microtransactions that are involved in that transaction. And that consensus allows us to have that consistency between either all going ahead or none going ahead instead of somewhere weird in the middle. Normally, what we use, a very common consensus protocol, is the two-phase commit. It's, again, shortened because we can't cope with multiple words, so it's called 2PC. But you can use other consensus protocols like Raft or 3PC, for example, three-phase commit. So when we're using something like this, here's an example using the package holiday that I had. So this is an example of sort of the issues I want to raise in terms of if you were to try and lift an ACID transaction from a more monolithic style application to a cloud-native microservice style one. So in this, we have some kind of front end sending the request through, which is just, we want to book a package holiday. We then have this coordinator in the middle who is collecting those votes for the consensus protocol. So that is our two-phase commit coordinator. And then for this, we have 3 microservices, one for the flight, one for the accommodation, and I'm going fancy, I'm booking a taxi. So we've got a taxi microservice. So in this, what happens is the request gets sent through to the coordinator. The coordinator, as the name suggests, coordinates all of the microtransactions. So it then sends the request to each of these microservices to ask, okay, you're involved in the transaction. I need you to lock your resources so that we can know whether they're all available or not. This is where that locking part of the ACID acronym comes in. So this is where we're isolating the resources. So in this period, no other transaction can come in and affect those resources or use them. So they're now locked, and they will then respond to say, we either have that resource or we don't have that resource. Depending on the response of, yep, confirmed, or no, we don't have it, that coordinator will then either say, okay, the transaction can go through because they're all available, or will say we need to cancel the transaction and roll back anything we've done within this transaction to be at the same state as when we started. So basically canceling it. Now, there are many issues with just lifting and shifting this to a cloud-native system. The first of those is the fact that for example, you're basically limited in terms of speed. So you are limited by the slowest service within that transaction, whatever that microtransaction might be, because you have to wait for all of them to go through before they're unlocked. So it is quite limiting, especially if one of your microservices were to go down, for example. The speed is very much limited. Another thing that's limiting is that you can't actually use two-phase commit with databases, for example, like RabbitMQ or with Kafka, which are often commonly used tools in cloud-native architecture. Other issues are things like communication errors or communication issues. So you are now relying on network communication instead of local communication, and that network communication isn't always reliable. Sometimes a message might get lost, it might go down. How are you going to check that that microservice received that message, or has it processed that message, or did it send a response, or did we lose that? So there's many ways in which this communication can break down, and you've got basically double the communication because you're having to go from the coordinator back and forth to this distributed microservice. Other issues are, again, we're in distributed environments now. Our microservices could go down, for example. And when they do go down, we're then, again, slowing down the overall transaction, but we're also at risk of potentially going down during the processing of that request. So then how do we know whether they processed it and gone through with it? Does the coordinator know? And it gets confusing, potentially, and also, again, slows down our request. And again, there's also the issue of your coordinator is also often now a microservice. So what happens if that single potential point of failure could become a bottleneck? It could become that single point of failure in your system. That can also go down and, again, affect the speed of your transaction. And whilst that's down, for example, your other microservices are still locked and no one else can then access that system. So your system is essentially unresponsive at this time, which is not great for cloud-native systems. You know, society as a whole generally expects their applications to be up all the time, no matter what. So there's a lot of issues with just lifting and shifting a traditional style ACID transaction into the cloud. However, there are alternatives that we can consider. For example, the Saga pattern. Again, we just love acronyms. So the Saga pattern is a failure management system where, again, it's still a sequence of local transactions, and they either all go through or don't go through. But in this time, instead of using the ACID principles that I went through, we're using a less constrained form of principles. So we're being a bit more flexible, but we are still trying to establish this consistency and allow this state to be sort of carried out using transactions. So in this case, we're using base instead of ACID. So base is basically available, soft state, and eventual consistency. Now, the key point here is the two that I've crossed out, and that's consistency and isolation. So the big difference between ACID and using the guiding principles of base is that you're losing that strict consistency because you're having to be a bit more flexible now. You're having to go with eventual consistency so that you can increase your availability. And that's why we have this sort of soft state and eventual consistency, because you're no longer isolating the resources, and so you have to have this eventual consistency. And this links in with the CAP theorem, if any of you are aware of it. If you're not, definitely check it out. It's very interesting. But this is essentially a theorem that describes that we can't have all three of these qualities at once. We have to choose which ones we're going to prioritize. And in this case, we're prioritizing availability over consistency, so we're more aligned with an AP system. If you really, really, really need consistency, but you're not so bothered about availability, then you'll be more aligned, for example, with a CP system, which is more aligned with that ACID-style transaction. But as we're going into sort of distributed cloud native, it's often that we need availability more than strict consistency. We do still need consistency, but it can be eventual. So the way that sort of the Saga works is that it's not, it's kind of different to ACID in that ACID has rollbacks. We don't have that concept within Saga. Instead, what it has is it's a forward strategy. So instead of reversing back actions that we've already taken, we do a different action that just so happens to compensate what we originally did. So that's why it's this forward strategy. And we call that a compensating action. Now, you can determine what business logic goes into that compensating action, but often it is essentially the reverse of whatever you did in the original action. So you can see examples here. We've got the blue, which are the actions, and the yellow, which are the compensating actions. So if we booked a seat as part of our transaction, then we'll need to unblock that seat at some point if we're going to reverse that if our transaction isn't able to be successful. So it is a forward-looking strategy. Now, there are two approaches when we're using Saga. We can either use choreography or orchestration. And it really depends on what kind of application you're using and how complex your transaction is as to which approach might be best for you. So the first approach is choreography, and you'll notice in this one, there is no central coordinator. So this is where each part or each microservice is involved in the transaction, essentially produces an event, and the next microservice that's involved in the transaction will act based upon that event that's been emitted. So your state is being transferred through the microservices as opposed to being stored in that central coordinator. Now, this is a great approach if you have a limited number of microservices involved in your transaction, if you have a fairly simple logic flow, and if you just want to get up and running straight away. It's very agile, and it can be really useful for that. But once you start getting into more complex styles of transactions, this can easily kind of snowball to become very complex, because the more microservices you add, the more you're sort of dependent potentially on the last one. It can cause cyclical dependencies and closer coupling between your microservices, so you do have to watch for that. And yeah, it becomes a lot more complex as you add more microservices. So if you've got more than, I'd say, like 3 or 4 microservices involved in your transaction, you're probably going to want to consider the orchestration as opposed to choreography approach. But this can be good just for getting up and running. So the alternative is orchestration. So in the orchestration approach, what we have is we still have this central coordinator. So this time we have a Saga coordinator, which, as the name suggests, coordinates all of the microtransactions. This is much better if you have more complex transactions, because you have that single point of truth, and you know exactly where the flow is going between your logic for each microtransaction. However, obviously, you do still have this potential single point of failure. However, the implementations of the Saga pattern have taken this into account, and they do have steps in place to try and negate the potential risk of that. So, for example, being able to easily restart it, for example, also being able to query the microservices to find out their status if it were to go down or if the microservices were to go down. Adding in these additional sort of behaviors, knowing that those microservices might go down, that network communication might go down, or that central coordinator might go down. So yes, you still have that potential point of, or bottleneck, or potential point of single failure, but you still have you gain the benefits of having that central point of truth and that clear business logic. So that's the second approach. Now, getting into how you can actually make use of Saga. So Saga is just sort of, as I said, just a general set of guiding principles, just like ACID was. So you will need some form of implementation that's based off it. And for this, I'm taking a look at MicroProfile. We're all at EclipseCon, so hopefully everyone is already familiar with MicroProfile. If you're not, definitely check it out. It's a great project. It is a community-driven specification all around developing APIs and specs to enable Java Enterprise or Jakarta EE applications to build for the cloud and build for microservices. So it offers, it's built by a lot of different people, individuals and vendors, and there's lots of different implementations out there. The one that I help work on is OpenLiberty, hence my t-shirt. And yeah, it's open source, and you can have a go with it if you want to. But there are others, like, for example, Quarkus, Wildfly. There's a ton of others out there. So the specs that are offered as part of the MicroProfile stack, this is the stack. This is 5.0, which is the most recent major release that's come out. If you're not familiar with MicroProfile, then I put a link here to, I've created a series on IBM Developer which goes through each of the specifications in this and explains them in more detail and gives an overview of what MicroProfile is. So you can visit that afterwards, or if you just want some extra reading, go ahead and read that. So in this, we have this sort of bottom pyramid shape. And for those of you who are familiar with Jakarta EE, you'll notice that there's some shared sort of APIs or shared specifications that are used here, like CDI, JAX-RS, JSON-P, and JSON-B. So there are some shared implementations. Then we also have some additional APIs that are really, again, designed for cloud-native applications. And this bottom pyramid is what you get as part of the standard stack. Now, as well as the standard APIs you can also get standalone projects. So these are developed and still built by the MicroProfile community, but they're just not yet part of that standard stack. It's hoped that one day they'll be moved into that, but there's no clear direction on that yet. So the one that we're really interested in today is LRA at the top there. Again, we just love acronyms. This stands for long-running action, and it is essentially an implementation of the Saga pattern. So MicroProfile long-running actions is what I'll be using to demo this today. So essentially, what this is it is designed specifically with the cloud in mind. So it is designed for loosely coupled, distributed microservices that are designed for the cloud. It is based on the Saga pattern, and again, it uses those more relaxed constraints of base rather than ACID, and it's basically a long-running orchestrated activity, a type of transaction. The goals of creating this was really to help simplify things like error handling when you have multiple services that are running as part of that single transaction. It helped to ensure the execution of application provided compensating action. So again, that forward strategy rather than using rollbacks, and things like allowing actions to finish early and making sure there's no strong coupling. So the example that I've got today utilizes OpenLiberty. Remember, with MicroProfile, it is still a specification, so you will need an implementation if you want to make use of it. And that's the implementation that I'm using in the demo today. If you're interested in finding out more about it, you can just head to openliberty.io. We've got a whole host of documentation, and what I would say is, more importantly, interactive guides. So if you want to get hands-on with some of this tech, any of the other MicroProfile specs I've mentioned, for example, you can head to our guides page on our website, and we've got an online environment you can use, so you don't even need any prerequisites downloaded locally, which is pretty cool. So when it comes to OpenLiberty, we are using the Narayana implementation of MicroProfile LRA, and we are going more along the lines of the orchestrated approach rather than the choreography approach. So in this, we have two different parts. We have the LRA participants, and we have the LRA coordinator, and usually they are deployed as their own microservices. So that coordinator will be its own microservice, and then each of those participants will usually be its own microservice as well. So when it comes to actually getting this up and running, this is my server.xml file, and as you can see, I've just implemented the MicroProfile LRA coordinator. Now, do bear in mind that obviously, I've tried to limit this to just the features that I need to make this as easy as possible to sort of understand and see. Now, I do still need CDI and JAX-RS because actually the MicroProfile LRA coordinator has dependencies on those two features. So if you are going to have a go with this yourself, just bear that in mind that you will also need CDI and JAX-RS if you want to have a go with this. Now, it's pretty easy to get up and running. All you need to do is LRA run and LRA start, and it will get this up and running for you in terms of the coordinator. When it comes to creating participants and making sure participants are aware that they're involved in the LRA transaction, we need to use annotations, as is often the case in MicroProfile specs. So for this, we'll need at least these three basic annotations. So you've got @LRA. This essentially just tells that particular microservice to either join or create an LRA transaction. We've got the @complete, and under this you'll have any business logic that you want to happen if that transaction is successful, anything that you want to happen as a result of that being successful. And then @compensate, as the name kind of suggests, this is our compensating action. So what business logic do you want in here if the transaction is not successful, in case you've already gone through with some of them? Because, again, this is eventually consistent, so you might have already locked some resources and then discovered, actually, my flight isn't available, so I'm going to have to unlock those resources or unassign them from this particular transaction. And so you might need to have that in your compensating action. So again, this is all about that eventual consistency, strong availability. So the way that it's going to look, this is all part of the same class. I've just kind of cropped it so you can see it all in one slide. So you can see I've got the @LRA annotation right at the top of my class, and any business logic I want to happen when it joins, the @complete annotation and the business logic there, and the @compensate. Now, if you want to check out any of this code, it is all available on GitHub, so you can check it out there. We've also got a blog which sort of goes through it in more detail in terms of how we're implementing this and how you can use it yourself and you can access that at the link here. I'll share my slides afterwards, so you don't have to take photos and type it in yourself. Now you'll notice in the @LRA annotation, I've also got this type that I'm using. Now this type is essentially what determines whether my microservice is going to either join or create an LRA. There are 3 different types you can use. There's requires, requires new, or mandatory. Now we're using essentially the middle ground here, so required. That means either if there's an LRA that exists already, just join that one. If no LRA exists, create your own. Requires new means that it can't join an LRA, it has to create its own every time, and mandatory means that it can't create its own, it's got to join one every time. So those are the 3 different types that you might be interested in, and depending on your microservice and your transaction and where it fits into that, you might want to use different types for different microservices. So there are other annotations that you can use. Those were just the basic 3 that you'll need. Other annotations you can use are @forget, @leave, and @status. And this is kind of what I was referring to when I was saying, being able to query, for example, to see what the status is for particular microservices if one were to go down, for example, or you lose some communication. So really adding in these extra annotations enables us to be a lot more agile and more aligned with cloud native principles. If you want to check out more about these annotations, it is in the documentation for MicroProfile, which I've linked to here, and you can read more about them there. But those are the basic annotations that you'd want to take a look at. As I said, this is all available in our demo app, which is available on GitHub, so feel free to head on over. It's based, again, on a sort of holiday booking again. This time we're getting a holiday, we've got a holiday microservice, a flight microservice, and a hotel microservice, all participants in an LRA, which is being coordinated through MicroProfile using OpenLiberty. So, in summary, I think I've kept to time. Yeah, I have. Perfect. So in summary, hopefully, my whistle-stop tour of transactions in the cloud has hopefully shown you that stateful microservices might not always be needed, but are sometimes still needed in cloud-native applications, and that traditional style transactions like ACID aren't necessarily the best tools to be using for cloud native, but that there are alternatives that might be useful, like, for example, Saga, and open source implementations of that, like MicroProfile LRA, to help provide suitable cloud native transaction tools. The nice thing is that you don't have to be paying for all of this. It is open source. Go and check it out. Contribute to it. Raise an issue if you want to. Yeah, go and check out MicroProfile LRA because it is a really interesting project and is maybe something that could help you if you want to do state within the cloud. As if I haven't given you enough homework already, if you want further reading, then here's some useful resources that you can take a look at. The first one is to that blog that I mentioned. The second one's to the GitHub repo. The third one's to the specification, the documentation. And the last one is, in case you want to take a closer look at Saga in general, we've got an interesting article on IBM Developer that you can check out that goes over that overarching sort of architecture type as well. And if you want to check out the open source projects that I've mentioned, there's some really useful links here, especially the starters. So if you've never used OpenLiberty or you've never used MicroProfile before, check out the starter application. It gets you started in literally like 2 minutes. Just select from drop-downs, and it will give you a zip file and basically an application that's ready to go. So definitely check those out if you want to have a go yourself. Or you can head on over to our guides if you don't want to download it locally and try it out in our cloud-native environment. Oh yeah. I'm also speaking again. So if anyone wants to come to those sessions, pop along tomorrow. I'm in different rooms. I can't even begin to pronounce those. I'm in other rooms, but come along tomorrow at either 12:30 or 4:15 if you want to learn more about open source developer tools, or we have a really cool project that we were doing with the Canadian universities all around really enabling open source with the next generation of developers. So come and check that out if you are interested in that. With that, I will say thank you so much for staying for the whole time. I hope you've enjoyed it. Thank you very much. If you do have any questions, I won't make everyone stay. Just feel free to come up and have a chat afterwards. Thanks, guys. I believe that the state is stored, so there's obviously state stored within your coordinator, which is storing the state of each of the microtransactions. but the state itself of each of the microservices will be stored in some form of like external database, for example, depending on how you architecture your application, based on like the availability of resources there.
So the individual microservices could still be stateless.
They could, exactly. Yeah. So it's not necessarily about you have to have state in every microservice. It's about how do you have state across microservices if they're all involved in one particular transaction thing. But you can still have stateless microservices that are involved in a stateful transaction. Yes, exactly. Yeah. Great question. Thank you. Anything else? No? I've just bombarded everyone with too many resources. Yeah. Cool. All right. Well, I'll just, I guess, smile for the photographer. Feel free to, have a break or stay here if you're here for the next session. Thanks, guys.